So we're going to talk about electrophilic aromatic substitution, which is a way of introducing a substituent onto the benzene ring in the first place, from unsubstituted benzene. And then we're going to talk about how to change one substituent into another substituent once it's on the benzene ring. Because there's a limited number of things that you can actually introduce into the benzene ring directly based on how stable it is. This is the most common reaction of the benzene ring. The mechanism for electrophilic aromatic substitution is incredibly easy, and fortunately it's exactly the same mechanism for any electrophiler. So fundamentally what you're going to do is you're going to take the electrophile, you're going to attack it with a pi bond, bond to the electrophile, put a positive charge on the carbon. That's resonance stabilized, but it's no longer aromatic. And this is aromatic. That's 4n plus 2 pi electrons. That's a closed shell. How would you characterize this intermediate? Anti-aromatic, aromatic, or non-aromatic?
I think it's anti.
What's the hybridization of that carbon?
Actually, never mind. It's not aromatic.
So this is now non-aromatic. It's no longer a cyclic pi system because we've introduced an sp3 hybridized carbon into the ring by making that new bond to the electrophile. So this is considerably less stable than that. You're going to introduce this as an energy diagram. Your cation intermediate is quite a bit higher in energy. So that first step is not very favorable at all. But then, in the next step, some base, and this base is often not very basic at all. Chloride, for example, is a strong enough base to do this. You're going to take this hydrogen off and regenerate the aromaticity. And that reaction is going to be effectively irreversible because the compound is now aromatic again. So restoring the aromaticity of the ring is the driving force for this reaction. So the energy diagram looks like that. The relative stability of these two things is not that important because once you've gone down here, you're not going back up over that energy point. It's very important when you do this that the carbocation ends up on the carbon that the electrophile is not attached to. Right? You can't have a carbocation here on an sp3 hybridized carbon. Carbocation is here. And it's very important that when you remove the hydrogen, you remove this one. And not this one. Right? Because if you were to remove this one, you would generate a carbene. And carbenes are not very stable, and you would not regenerate the aromaticity. Right? You have to convert this sp3 hybridized carbon back into an sp2 hybridized carbon in order to regenerate the aromaticity. So this is similar, kind of in overall effect, to nucleophilic acyl substitution, where we start out with an sp2 hybridized carbon, and then we form a bond to make the tetramethyl sp3, and then we take a hydrogen off to regenerate the sp2. But instead of the negatively charged thing being the thing that attacks and then leaves, it's the positively charged thing that gets attacked and then loses the proton. The two common mistakes, some of you are probably going to make it next Thursday, are putting the positive charge on the wrong carbon, right? It's got to be on the sp2 hybridized carbon, not sp3, and taking off the wrong hydrogen. So try to avoid those two errors. And that is why I drew both of these hydrogens in, right? To make sure that I kept track of which one was the sp3 hybridized carbon and which one was the sp2 hybridized carbon. If you don't draw the hydrogens in, sometimes you lose track of what's going on. So this mechanism is easy, right? You can't get this wrong. Attack the electrophile, take the proton off, regenerate the aromaticity, life is good. What's complicated is this is an aromatic ring, right? It's pretty unfavorable. So in order to get that reaction to go at all, your electrophile has to be really good. The electrophiles that you're used to attacking with the regular pi bond just aren't going to be good enough. So normally bromine, right, bromine would react, and you'd expect to generate a dibromide. It would go through the bromonium ion as an intermediate. But bromine is just not a good enough electrophile to break the aromaticity. This bromonium ion would break the aromaticity. You have 2 sp3 hybridized carbon, and this is not a good enough electrophile. So how can we improve the electrophility of bromine? If we want to take benzene and make from it bromobenzene, notice that we're only replacing one hydrogen, right? So we're making a monobromide, not a dibromide. What electrophile can we put in there that's going to be strong enough, that's going to be powerful enough to react? We need to make bromine more positive. This is, right, you can have bromine, molecular bromine, if we form a instantaneous dipole, it looks like this. Right? Caused by polarizability. But that's not a very large amount of positive charge on one bromine. So what we do is we add bromine, molecular bromine, but we activate molecular bromine by adding a Lewis acid catalyst. And a common Lewis acid catalyst that's often used for this reaction is FeDr3, or ferric bromide. Also known as iron-3 bromide. And it's got to be anhydrous. You could buy ferric bromide as a hydrate, but we need the anhydrous ferric bromide. Anhydrous ferric bromide is a very powerful Lewis acid. There's iron in a +3 oxidation state, so relatively high oxidation state of iron. So bromine will actually bond to the iron. This dramatically increases the electrophilicity of that bromine. And so this is the electrophile. It's complex between bromine. You'll notice that this part looks like a fairly stable complex ion. If we break this bond by attacking that bromine with the pi bond, we can generate our intermediate cation. And that's broken the aromaticity. And we also generate what looks like a stable tetrahedral complex ion. Formal charge is minus on a bromine or an iron. So even though this bromine is the one that has the positive formal charge in the Lewis structure, it's this bromine that gets attacked in order to return this pair of electrons to the bromine and generate this complex ion. Just to recall for just what's the name of that complex ion. So we're taking ferric bromide, reacting it with molecular bromine, and essentially generating Br plus. We're not generating Br plus like 6 electrons with a positive charge just on one bromine, but we're generating a molecule that acts like Br plus through the stability of this complex ion. Anyone? Four bromines. Tetrabromo. It's an iron. Ferro, right? Yeah, ATE, so it's tetrabromoferrite. If it were cobalt, it would be tetrabromocobaltate. But because it's an anion, we use the Latin root on the name. So this is the tetrabromoferrate ion. And we need to put the oxidation state on the iron in parentheses afterwards. So this is tetrabromoferrate 3. And then the counter ion obviously is this. So what's the base that takes the hydrogen off? It needs something. What's that?
The complex taken?
The complex. There's nothing else that's negatively charged or basic in there. So what's going to happen is one of the bromines from the tetrabromoferrate is going to yank that hydrogen off and restore the aromaticity. So these two steps are same, right? We have a powerful electrophilic that's attacked by the ring, generating the carbocation intermediate, which is quite a bit less stable, now non-aromatic. And then we take a hydrogen off to regenerate the aromaticity. And we also regenerate FeBr3. So this is catalyst. It's not actually part of the overall balanced equation. So if you're the kind of person who likes to write note cards, you would write it like this. And then you would memorize that reaction. Bromine and ferric bromide catalyst. It's not the only Lewis acid catalyst. Other Lewis acids will work. Basically what we want is a metal or a non-metal in a high oxidation state, and bromine's on there, right? So we don't have multiple different halogens. So standard bromide would work. And Aluminum bromide would work. Aluminum bromide is actually an interesting molecule. AlBr3 doesn't really exist. It exists as a dimer. So whereas AlCl3 is actually an ionic solid, AlBr3 actually exists as Al2Br6 and it's molecular. And you can boil it, it's a liquid, right? But it'll work, it'll act like AlBr3 in solution. So basically any metal in a high oxidation state with bromines on them or halogens will work. It's also not limited to just bromine. The same reaction can work with chlorine through a mechanism that's very similar. With an appropriate Lewis acid catalyst, it's Cl2, and let's just use SFCl4 there for the halogen, right? Antimony also works, so SbCl5 would be another Lewis acid catalyst that could work for that situation. So what you want is you want a halogen, you want a Lewis acid for that halogen to react with to form a complex that's going to have this metal halogen-halogen bond. It's going to make one of those halogens significantly electrophilic. So chlorine would be activated by SnCl4 in the same way the bromine is activated by FeBr3, chlorine would attack it, and you would generate an intermediate looks like this. Charge of metal, and then your bromine or your benzene ring would attack that chlorine to generate something like that. Ion. Now, what would the name of that one be? Pentachloro, this is chlorine. SN. Stannate. The oxidation state on tin in stannate, which comes from stannate, right? So this would be stannate chloride. So the pentachlorostannate 4 ion is also a nice stable complex ion, which allows this chlorine to come off. But the pentachlorostannate ion can donate a chlorine, regenerate the aromaticity of the ring, and regenerate the catalyst. So all of these reactions are catalytic in the Lewis acid. The Lewis acid is simply there to activate the halogen by bonding to one end of the halogen and thus generating a electrophile that's much more powerful than the halogen atom itself. The more polar the metal halogen bond in the ingredient, the more polar this is, the better this reaction is. So since chlorine is more electronegative, that's a more polar bond. This can be used to put iodide and fluorine on rings too, but it is actually not frequently used to put those. Fluorine is a pain in the ass. The reason you wouldn't want to use molecular fluorine and a Lewis acid catalyst that has fluorine on it is not because it wouldn't work well. It would. It's because fluorine gas is corrosive and poisonous and really nasty shit. It actually dissolves, reacts with the glass vessels. So you have to use platinum vessels. And fluorine is toxic. So if any of it escapes, you're in trouble. The first several chemists who tried to isolate molecular fluorine ended up killing themselves in the process because they got exposed to the fluorine. So you don't want to work with molecular fluorine. Usually you want to make the fluoride from something that's more benign. So halogenation, right? We can halogenate a benzene ring, which is probably not surprising, right? Because halogens are electrophilic, and we already know about halogenating ordinary double bonds. What else can we introduce directly to a benzene ring? One of the most common and useful is nitration, where we take a benzene ring and substitute it with a nitro group. If you put enough nitro groups on it, it'll become explosive, so that's handy. And the reagents for this are concentrated nitric acid, 71%, and concentrated sulfuric acid, 98%. So we try to minimize the amount of water by using a mixture of concentrated aqueous acids. If you heat it up enough, right, it'll put one nitro group on there without being heated. But if you want to put multiple nitro groups on there, you can do the same reaction. Another reagent that will do the same thing is fuming nitric acid, which is concentrated nitric acid into which you have bubbled NO2 gas. And then you can put multiple nitro groups on. You can make 100% nitric acid from this mixture by distilling it. If you take a mixture of concentrated sulfuric and concentrated nitric acid and heat it up, you will distill out 100% nitric acid with no water present. It's really nasty. We used to use it in the organic lab to do a nitration reaction, and the student got it on themselves once and didn't realize how bad a thing that was. And he basically, he looked like he did it with a knife, but he had this huge welt all the way across the back of his hand. So we don't do that reaction anymore. He came in, I had him come in the next year, show his scar, and point out that it was probably important to wear your gloves during the reaction. So the question is, what's the electrophile? And how do we generate it? Because once we generate the electrophile, we know how the reaction goes. The benzene ring attacks it, forms that sp3 hybridized carbon, breaks the aromaticity, and then some base comes in and yanks off the other group. So what's the electrophile? To figure that out, we need to be able to draw the structures of nitric acid, sulfuric acid. And remember, these are oxyacids, so the hydrogen is not attached to the central atom. I shouldn't have to say that, but I know that I do have to say that because someone in my lab section drew sulfuric acid with 2 hydrogens off the sulfur. I think I should have been able to damage them again for that. Sorry. Go back to 110. So sulfuric acid looks like that. It's got 2 pi bonds to oxygen and 2 OH groups. Nitric acid looks like that. Obviously, this is another resonance structure for nitric acid that has a double bond to this nitrogen. Positive charge on the nitrogen, negative charge on the oxygen. We can't do this with nitric acid because nitrogen is incapable of expanding the octet. Right? There's no d orbital present in the n equals 2 shell, so you can't make 2 double bonds. So what do you think might happen if we mix together that and that? There's a little water present, but not a whole lot, so the water is just kind of sitting there watching. do you do?
Can the oxygen with the negative charge and the nitrogen attack the sulfur and break, or no, it's going to take the A.
Let's just protonate the nitric acid. That'll generate a really good acid. And nitric acid is already a strong acid. Protonated nitric acid is probably even stronger acid. You could reasonably expect this equilibrium to lie after reaction, right? Because H2NO3, pretty damn good acid. It's not very stable. What can happen is it can break down to lose water. And generate nitronium cation. And that nitronium ion is a really damn good electrophile. NO2 plus, not very stable. Once you've generated NO2 plus, I think you know what the nitrogen looks like, right? Really damn good electrophile. Ring's going to attack it. Break one of those nitrogen oxygen bonds. Generate an sp2 hybridized carbon and a now non-aromatic structure. And then we need to take off a hydrogen. Not this one. This one. Not this one. Never this one. So what's the base? It's going to take that hydrogen off.
Can it be the sulfur?
You've got two logical choices. One of them is the hydrogen sulfate ion. The other is water. Right? 6 to 1, half dozen of the other. We know that sulfuric acid is a strong acid, and so in the presence of water, it's getting protonated anyway. So I'm going to use water. On the principle that there's probably more water around than there is hydrogen sulfate ions, right? So water is likely more abundant. But if you use the hydrogen sulfate ion, that's fine too. Wrong with that, and that would generate the hydronium ion, which you'd expect to be present anyway, right? If you have sulfuric acid in solution, you don't really expect there to be any sulfuric acid in the presence of water. It's a strong acid, you expect it all to be protonated to water. Now, granted, in concentrated nitric and concentrated sulfuric acid, there's not enough water to protonate to dissociate all the sulfuric acid, but you probably have hydronium ion present as well. Hydronium ion is a weaker acid than sulfuric acid, so it's likely that this is the acid in the first step. But it's not crucial. So pretty easy. Once you generate the nitronium ion, addition, and then regeneration of aromaticity by deprotonation. And it's just 2 steps to regenerate the nitronium ion, protonate nitric acid, and then intramolecular decomposition with loss of water. So it's still a pretty easy mechanism. It's still only 4 steps. The beauty of nitration is once you have a nitro group, that nitro group can be converted into a ton of other different things through other reactions. So this nitration reaction is pretty easy. You just mix together concentrated acid and keep the piss out of it. So there are as many nitro groups as you want on there. And you try not to blow your cans off if you're trying making like a trinitro compound. Because all the trinitro compounds are explosive. TNT is trinitro polyamide. Trinitro is explosive. So generally when you're doing a nitration reaction, you put a big plexiglass shield in front of your reaction so that you don't blow your hands off. So nitration. Another group that you can introduce readily is the sulfonate group. To make a sulfonic acid. In this case, benzene sulfonic acid. And the reagent for that is fuming sulfuric acid. And that's concentrated sulfuric acid into which you have bubbled SO3 gas. Nasty stuff. SO3 gas reacts immediately with water to form more H2SO4. And that's actually what happens in the atmosphere to generate acid rain. So there's no water present anymore. You have liquid sulfuric acid with SO3 gas dissolved in there. And SO3 gas is remarkably soluble. You can make up to a 65% by mass solution of SO3 gas in H2SO4. It's not that stable. As soon as you take the cap off, SO3 gas starts billowing out of the thing as a white acid, reacting immediately with any moisture it finds, including you, if it finds you. So it's not a nice reaction, but it's a good way of putting an SO3H group on the ring. And these sulfonic acids are important precursors to sulfonyl chlorides. And you'll remember that we used sulfonyl chlorides like this, specifically this one. Which is parachloride sulfonyl chloride. As a way of making a hydroxyl group, which is not a leaving group, into a tosylate, which is a leaving group. The reagent that accomplishes this is PCl5, solid. And so we mix together basically the acid chloride of phosphoric acid. PCl5 is a really reactive source of phosphorus, and that'll generate the sulfonyl chloride from the sulfonic acid. So what's the electrophile in the reaction of benzene with fuming sulfuric acid? This is what's in solution. Sulfuric acid, SO3 gas. Take a break after this one. Okay. So what's the electrophile? Both of these are sulfur in +6 oxidation state, right? So which is more likely to act as a Lewis acid, SO3 or H2SO4? There's a reason why I drew the SO3 closer to the benzene than the H2SO4.
How's the SO3?
That's the electrophile. And it's a really good electrophile. And if you ever wonder kind of, which is the better electrophile, just draw the resonance structure. And applying the great rule of organic chemistry #1, draw the minor resonance structure. That minor resonance structure has a 3+ charge of the sulfur, which is a pretty high charge. You can't generate a resonance structure with a 3+ charge of this one. The maximum charge you can get on that sulfur is +2. got some hydrogens in there. So, looking at the minor resonance structures, it's evident that SO3 is the more powerful electron. Intermediate chemicals like this. This charge on the carbon the sulfur is not attached to. And we have to worry about what's our base. And in this case, we have to worry about which step we want to do first. Because we need to take a proton off the benzene ring to regenerate our electricity, but we also need to add a proton to the SO3 minus group. Which are we going to do first? Are you in acidic solution or basic solution? Acidic solution. In acidic solution, you want your intermediates to either be positively charged or neutral. So what we want to do is protonate that first. And that generates base that we use to take off the. In this case, there is no water present, so the logical base to use is the second sulfate ion. So it's one step longer than your typical reaction because we've got to put this proton on. You get the same product if you did these two steps in the opposite order, but doing them in this order generates a positively charged intermediate, and doing them in the other order we generate a negatively charged intermediate, and in strong acid, generally you want your intermediate to be neutral or positive. So we can put a sulfonate group on it. Let's take a break, and then we will talk about how to make carbon-carbon bonds.